Well, welcome to Secrets of Success podcast with Dr. Shay Needham. It is a pleasure to have you today, and we're going to talk about some science. We have a lot of listeners who aren't mass spectrometrists and aren't scientists, so we want to try to keep things at a level where they can understand. Yeah, I know you have some exciting news about NASA and so on and so forth. Let's get some introductions out of the way first. I am Dr. Shay Needham. This is the Secrets of Success podcast with myself, where our theme is actually never be outworked. We talk about science, we talk about relationships, we talk about bodybuilding, weightlifting, powerlifting, um, anything with a hard work ethic and a mindset, and you're going a never be outworked mindset. You're going to hear from Mazdak today, who definitely has a never be outworked mindset. And by the way, for those of you who are listening and just made a comment, play some rock. You will hear on my intro video that last part of the last minute of that intro video is a custom tune by an awesome friend of mine who actually wrote a custom song for me, and it's definitely rock inspired for sure. It might not be heavy metal, but it's certainly rock inspired, and I love it. It's perfect for the podcast. So thank you very much. Again, welcome to the Secrets of Success podcast. You can follow me on many social media platforms, including Instagram, Facebook, LinkedIn. You can also follow me and see all the previous episodes of these podcasts on YouTube, on SoundCloud, on Spotify, and also on iTunes. So see us there. You can also see streaming at the bottom of this banner of the webcast here is the website, drsneedham.com. Go there. You can learn more about me, see the previous podcasts, and see some other information as well. Thank you very much. It is a beautiful day in this beginning days of November, and it is beautiful here. It's sunny. I don't think there's a cloud in the sky. I'm looking at Moscow Mountain right now, and from Moscow, Idaho, it's just a beautiful, beautiful view. Thankful for all you viewers that have been giving us great opportunities, great engagements online, and we're seeing thousands and thousands upon them, especially on LinkedIn. Have a really big week. We have a lot going on this weekend with presentations and topics and conferences and so on and so forth. So thank you very, very much. Again, Mazdak, it is a pleasure. I want you to introduce yourself, start wherever you want to, however back far as you want to, and to what you are currently. So, and talk about anything you want, not just being a scientist, but everything that makes you well-rounded. So again, a pleasure. Thanks for being on the podcast.
Hi, Shane. Thank you. Thank you having me on your podcast. And again, I've listened to some of your podcasts, and they're really interesting, and it's kind of engaging to follow your topics. Yeah, my name is Mazdak Taghioskoui. Probably it's a my first name is kind of easy. The way I explain that is like Mazda the car with a K at the end. My last name, I have to apologize anytime I'm pronouncing my last name over the phone. You can imagine for customer support, it's like I have to stop and apologize. I usually go with Maz, so probably that makes it much easier. And basically I can say that a mass spectrometry instrumentation scientist, that I love making mass specs. And probably for as you mentioned, those who kind of are they don't have a background in mass spectrometry, it's a basically instrument that you can weigh molecules very accurately. And obviously, it has a lot of applications from the food that you eat to tests that you might take a doctor's office to these missions that NASA has for different planets to look and see the chemistry. It's everywhere, and basically, I think that would give enough background to the audience.
Well, tell your story. So I'm not sure. I think we somehow met on LinkedIn or something. I saw a post of yours or a common colleague or something. I'm like, wow, with the technology that we'll talk about in a minute, that's cool stuff. And I'm like, I want to hear more about it. I think that's how we met. But just describe that process, how we met, and describe what your company Trace Matters does and what you've done. And you're an entrepreneur. You're the founder of Trace Matters, and talk about that story. How long have you been an entrepreneur? when did you start the company? What have you guys been doing? Talk about that.
Yeah, I think we met on LinkedIn, and probably mass spectrometry community is not that small, but it has a bar that if like we're well connected, even though we haven't met before. But if somebody shares something mass spec related on LinkedIn, I'm interested. I'd read that, and probably I'm going to reach out to the person. And I think that's how we met, because again, it's a it's a field that it's kind of special. It has a special community, and probably it's I like to say that it's very addictive. So when you start using a mass spec, or when you start to really understand what a mass spec is, you're really amazed with the power and the complexity, and you just want to work on that for the rest of your life. So it's really addictive, and probably that's kind of a common team that connects mass spec people to each other, and probably that's why we got to connect to each other. And just to tell about briefly about myself, I basically have background in chemistry and electrical engineering, but I see myself as a chemist, and like from childhood in high school, like I had my own chemistry lab, and I was playing with acids and all these chemicals when I was a kid.
Awesome.
I burned my hand. So back then we didn't really have safety protocols, and I'm kind of lucky today that I'm not blind, because I remember pouring acid on base one day, and it was explosion to the wall, and I was lucky that it was not facing myself. So back in old days, you really it was really easy to play with the chemicals. But again, it's much better now. At least you know the dangers and everything. But again, then I started my undergrad program back in Iran in electrical engineering, and but I always had that passion of being able to measure the chemistry and turn it into electrical signals. And that's why I kind of switched back and forth between chemistry and electrical engineering. So I did my bachelor's and PhD in electrical engineering, and my master's and postdoc in chemistry, analytical chemistry. And basically engineering give me tools to be able to really make instrumentation.
Well, certainly, that's what I've always loved analytical chemistry myself, and not as engineering as much as applications. Like you build things, but I worked with a lot of people from University of Michigan, from Florida, from Purdue. You recognize all those top names, right? And all those professors, and they're chemists, and they were in a chemistry department, but they knew how to build things. They knew, it's like they had this engineering knack, but a chemistry background. So it's a lot like you. Now, so you had your bachelor's degree in Iran. Then did you do where'd you do your master's degree?
I did my master's and PhD at George Washington University. So I came here for my grad school. So So basically,
so you did your master's in chemistry at George Washington, and then you went on to get your PhD in a different group, I'm assuming, with electrical engineering.
Yes, it's in a different group. So I did my PhD in electrical engineering, but again, my dissertation, my research topic was mostly plasma ion sources, which basically producing these low pressure or even atmospheric pressure low power plasma sources that they can be used for producing ions for mass spec analysis. And probably it's a good time to say that like mass spec has three main components. You have an ion source, you have an analyzer, and then you have a detector. Obviously, it's very complex, but in simple terms, it's like these three main modules that for me, it was mostly producing the ions so that the rest of the system can analyze that.
So describe to the non-scientists, why do you have to make an ion, and describe kind of how that works, because we're going to get into your awesome trademark technology that's NASA is using. So describe why you have to make an ion. and describe that process of making an ion from something that everybody would know, like a simple molecule, an example or something. And why do you make it an ion? So then you can detect it. Kind of describe that process, Maz.
Say, like, I'm a very practical person, so I want to really talk like from a practical perspective. So imagine, for example, you have a $20 bill and you want to see if it's contaminated with drugs or not. So the first way of like using doing that with a mass spec is somehow you need to take out some molecules and to be able to feed this to this instrument for the instrument to tell you what it is. And like the first step is to produce gas phase ions. So to take a molecule and produce a charged particle in ambient air or in high vacuum, so that the rest of the system can function. And the way it works, it's really simple physics that if you have a charged particle in an electric field, then the trajectory, the electric field is going to have some effect on the charged particle. And like with some special waveforms or some special voltages applied to your electrodes, you can basically separate them based on mass to charge ratio. And again, the first step is to be able to very efficiently and effectively transfer your molecule, for example, from that bill to a gas phase ion, so that it can go inside the instrument.
So basically, you have to produce an ion so then you can control it and detect it. Would you say that that's accurate?
That's very accurate. Exactly.
Okay,
So again, over the years, I've seen this one-to-one analogy between photons and ions. There are many differences, but again, it's a good analogy that, for example, the same way that a prism separates photons based on the frequency or wavelength, a mass spec is basically it's this the counterpart for doing the same thing with ions. So if you have a mixture of ions, so a mass spec is a prism that separates them, and based on your detector, you can really see what type of ions you have in your ion beam.
I'm glad you talked about mass spectrometry. I was thinking you were going to talk about the duality of light, but let's not go down that road.
Yeah.
So anyway, that's really fascinating. That's really, so you graduate with your PhD in electrical engineering. What year was that? And then what was your next step?
It was back in 2011 that I got my PhD. And after that, I tried to, during my PhD program, I was really using these mass specs, they were basically, they're like a black box that you can't really know what's happening inside. So, but I had access to the front end, and that was the only access that I had till I got my results from on the screen, basically from the software. And after that, I got interested to learn about like what's happening to ions inside the mass spec. So again, naively, I thought maybe making one is going to be easy because the theory is kind of simple. So I started building my own mass spec, and that was really the reality hit me hard that it's not that simple. It's difficult. Yeah, and from there, I just kind of, the story of trace matters started, and yeah, now I'm talking with you. Yeah, and
your company is Trace Matters. So when did you incorporate?
It was almost back in 2013.
Yeah, wow, that's incredible. So for those of you that are watching, if you look at Maz's background, he is in a lab, and this guy loves to work in the middle of the night. You can tell he loves mass spectrometry. You can tell he loves making ions. And so if you look at his lab in the back, he is active in his organization. And we'll talk more about some of the work that he's done with NASA and some other organizations as well. But you can just hear the passion in his voice. And that's what an entrepreneur needs, and persistence. We'll talk about some of that as well. So what a great story. So you start Trace Matters. and you're like, okay, you're going to make these. What should we call it? An ion source? What or ion sampler? What do you call like a spy-on device?
Spy-on device is what I would describe is just right after the ion source, and that's it's kind of correlated to my journey that I started with an ion source. So I started navigating inside the mass spec, and the first thing that I started making was the ion funnel and ion guides that they're at the first vacuum stage of a mass spec. So it happens like that. If you just imagine you're walking into a mass spec, the first thing that you'd see, it's going to be an atmospheric pressure sampling inlet, and after that it's going to be an ion guide or ion funnel. And I was spy-on, it's a re-engineered version of that section of a mass spec.
So in general, let's just talk to the audience about this. In general, you have a mass spectrometer. Let's say this mass spectrometer we'll use US base units. So we'll say it's 2 feet by 3 feet. Okay, that's the size of it. And your ion source is directly connected to that. What spy-on is it's a device where you can sample remotely, so to speak, a long ways away from the mass spectrometer and get the ions into the mass spectrometer. Is that correct? Is that how you would describe it?
Yeah, exactly. So probably a simpler way to describe that is that first, probably we have to give some background that those ions that we produce, they need to reach high vacuum, because in electric field, if we don't have high vacuum, probably the collisions with the air molecules, they're not gonna. The collisions are not going to let us have a good separation of ions. So we really need to have high vacuum so that the ions can travel without any collisions, so that we can really control them and separate them. And like every mass spec, usually we take the ions from high vacuum in most of them, and then we should transfer them to the high vacuum, and then the detector is also in high vacuum, and then we detect them. But again, if we go back to that analogy between the photons and ions, photons, they travel in straight line. It doesn't matter if it's in air or vacuum, they travel in straight line, and it's easy kind of to observe them. If it's in visible range or IR, basically you can put a piece of paper and see your beam. But for ions, it's not like that. The only access that we have to monitoring the ions is basically reading the ion current. So you have to put an electrode and measure the amount of current hitting that. And that's basically makes a mass spec much more complex than an optical setup, that the ion transfer from one stage to another stage is not trivial. So if you want to transfer those ions that you've produced in atmospheric pressure to the first vacuum stage, a lot of them are being lost in that heated capillary. So each stage has its own transfer efficiency, that at the end you get like less than 1% of your actual ions that you've produced. So basically the role of a spy-on is to make sure that when we produce that ions and when we have it at the first vacuum stage, basically you can decouple the ion source from the mass spec and still maintain the high transfer efficiency.
What is can you measure the transfer efficiency, and what is that number?
The transfer efficiency is, for example, you can measure the amount of ions that your source, for example, if you have electrospray source, so you can measure the amount of current on that source. Then you can measure the current after your heated capillary inlet. Then you can measure the current you're at the exit of your ion funnel, and just those ratios, it's kind of telling you how much ions are being lost at each stage.
And but so again, what is the percentage, or is it dependent?
It's the percentage. Ideally, you want to have 100%, but right. Like the bottleneck at this point, I think from what I've seen is the heated capillary inlet, that almost 99% of your ions is being lost at at that transfer. And after that, the transfer efficiency still remains high, above 50%, or at some.
Interesting. So you're saying that actually you lose almost 99% of them just getting them into the SPION device?
That's correct, and that's all in almost all of the state-of-the-art instruments that they use, like heated capillary. It's high. The double cone structures, a little bit better, but again, you lose a lot of your ions, a very high percentage of your ions at that transfer.
Now, so let's talk about that, because I think mass spectrometry, I'm sure you probably think the same thing, and we're probably biased because it's our industry, but it's going to replace and complement. It is, I would say, the major measurement tool right now, and I think it's only going to increase its capacity and use in all applications. One of the big issues, though, if you think about electrospray, or that's what I'm familiar with, or even APCI, is that you do lose on that front end. You lose a high percentage of your ion current just getting it into the sampling device. And so can you describe how you're sampling? And I'm going to try to understand it and kind of relate it to ESI, for example. And then we can try to get in. I want to understand scientifically why you're losing such a high percentage. So describe that process.
Basically, that process is that when you produce your ions at atmospheric pressure, you can't, for several technical reasons, you can't just in one step go to high vacuum of -5 torr or something. So one reason is that we don't have a single pumping technology that can go that high. And the second reason is that it's like you have to go step by step to be able to not lose ions, to be able to control the loss of the ions. But again, the only technology that has been there, it's called a heated capillary, because basically it's a long, narrow tubing, which the idea of that, it's like 500 micron to probably 1 millimeter. That, like, different manufacturers, they use different sizes, but that correlates directly to the size of your pump, because if you're or if this is larger, it's going to have higher efficiency, but the pumping requirement is going to be increased with that. But again, that has been around for a long time, and I haven't seen any good solution for that problem. Probably MALDI solves some that problem, but again, MALDI has its own problems, that basically you put your sample in high vacuum to be able to have very high efficiency.
So, I mean, one of the things and I'm just trying to, and then we'll move on, but I'm trying to understand myself with the SPION device, or sampling into the SPION, for example. One of the things that you can do with ESI, and I'm sure you're probably familiar with this, is as you go to a lower flow rate with your liquid sampling device, whatever that is, HPLC or whatever, a lower and lower flow rate will give you a higher transmission efficiency. So is it just that getting ions into the mass spec, into the SPION device through the heated capillary? Is it the flow rate, whatever that flow is too high? Can you slow that down and increase the transmission efficiency?
That's a very good point. Probably it gets a little bit more complex, because I think you're talking about nanospray. For nanospray, when you produce your ions, nanospray is very efficient in producing the ions, because when you have, like, you can imagine that your molecules are coming out of the tip of the electrospray, and you have a limited amount of charge to be able to charge them. So if you decrease that flow, then probably the ions are going to have more, are going to get charged more, and that's why you see an increase in the efficiency. But this happens after the ions are produced with the electrospray, and they're gas phase, and they're right in front of the inlet. So that inlet with suction takes these ions in, and the most most of the ions, they get lost with collisions with the inner walls of the capillary tubing. And for that transfer from 760 torr to almost 1 torr, the capillary inlets, it's been almost the only available solution, but which they're working. But again, probably I should note that Um, Probably you don't need a lot of current because, again, going back to the analogy between photons and ions you can't really, you hit a space charge limit that if you have so much ions, they start diffusing each other and they start like repelling each other, and you basically like more ion current is kind of, it's not to your advantage. So there's an
Isn't it true? Sometimes more ion current just leads to more noise and less to noise. And so, anyway, fascinating. We could talk about this for hours.
yeah.
I love it. I really do. And you're onto something. So, I want to hear more about. So, tell us about this spy-on device. So, it's like, how long is this the typical spy-on device where you're going to be? I look at it as and you guys can go see it on his website, tracematters.com. It's like a big tube that you can put ions through. It's an ion funnel, so it will funnel ions from one location to another. So I'm going to give you two examples, and he's going to talk about both of them. One way that this could revolutionize sampling is, for example, a surgeon working on a tumor. Tumors have certain characteristics that other parts of the tissue in a body don't. And right now, what surgeons do when they go in and they see a tumor, they do exploratory surgery, they cut somebody open, and they're using their eyes to say, this is where we have to cut. And it's very invasive, and you usually cut way too much, so you cause a lot of irreversible damage to the patient. One of the things that mass spectrometry has done in recent years is that you can sample around that tumor to see exactly where the surgeon can use this surgical knife to cut. And so you can basically, instead of the surgeon having a mass spectrometer on top of the patient, he has this big long hose that maybe 10 feet long, 20 feet long, and it samples the tumor and sends it into the mass spectrometer across from the operating room. And so, phenomenal. That's one example that I would like to hear more about. The other example that Mazdak has just won an award for is he won an award for NASA for designing this ion funnel that is possibly going to be used for the next trip to Mars. Incredible. It's awesome that I'm even talking to you. So just incredible technology. Can you describe both of those scenarios and how Spion could be used, that long ion funnel, to revolutionize this type of sampling, actually?
Yeah, I think the most important value that Spion is basically bringing to the field is that, like back to our conversation, mass specs are like a solid box that, because the ion transfer is not trivial, you have to they spent years and years on optimizing each the ion transfer in between the stages, and usually they're all connected to each other. So ions should be produced right in front of the inlet. People have tried to just do remote analysis by using a bare tubing. So you have two options. Either you have to send your molecules in neutral form to the inlet of the mass spec, do the ionization there, and then do the analysis, or just produce the ions next to your sample and then transfer the ions to the mass spec. And each one each architecture has advantages and disadvantages. But producing the ions right next to being able to just take your inlet and bring it to next to your sample, that has huge advantages. One is probably you eliminate any cross contamination, because the ions are you can control them with the electric field, but so you'd be sure that there's no cross contamination. Second, it's going to be much faster. And third, you can really use what's called like ambient ionization, which was introduced back in almost 10-15 years ago, and it has huge potentials. But again, just by not having a tool, a means to transfer the ions from your sample to your mass spec, that has been holding ambient ionization back. Because ambient ionization, a promise is to do the analysis with the sample in native state. And the native state, for example, can be a patient. with the current instrumentation, we can't really have a mass spec next to a patient. Even if you have a mass spec next to the patient, again, any part that needs to be analyzed, it needs to come and contact the mass spec, which usually that inlet, the conventional inlet, has high voltages, is heated to like 300, 200, 300 degrees C. So there's many problems associated with that. And again, the bare tubing, it's probably you lose all of your ions. Probably you lose more than 99% of your ions. It's
exciting. What's exciting about Spion and a device like that for sampling a patient, for example, with oncology, with cancer, is you think about the process now. What does oncology diagnosis look like? So the patient goes in, they do surgery, they cut around a tumor, they remove a tumor, and then they send it in for pathology, and they wait a day or more.
It's at least like 2 weeks to get the report.
Right, at least, right? And so then they get the results back, and they'll be like, well, I guess we didn't get enough of it. We'll have to go in and do more surgery. And so to have this I've been dreaming about real-time and patient-centric mass spectrometry for decades. And we're getting there. There are still some challenges. I hope we get to that in this podcast. I want to hear your ideas. But I think that's really critical to think about the patient and how much that could improve the patient's quality of life. That could actually, in a lot of ways, it could reduce costs, which is very important in our medical field nowadays. Cost is huge. The current trajectory we're on is not sustainable, no matter who pays for it. And so it's really, really cool that this technology and mass spectrometry and technology you're developing is a part of that solution to helping patients. So good job there. What do you see the future of that for patients? And then let's get on to talking about your NASA project. But what do you see the future of mass spectrometry with patient-centric analysis like we talked about?
Well, I should first note that I don't have any medical background, so all the things that I'm going to tell, it's basically what I've learned from my collaborator at Harvard, Professor Natalie Agar, that basically these types of projects, it's really so complex that each group and each person is bringing one piece of the puzzle. So we need to really have a tremendous amount of people to be able to make something like this possible. And I can like mostly my job is on the instrumentation side. So Professor Agar, she's probably I should start with their infrastructure that they have there. They have an operation room called Amigo, which basically it's a research grade, but it's the world's most advanced operation room. And in the room, they have MRI, they have all these different research grade tools so that they can use actually during surgery to be able to just introduce something new. And Professor Agar, she's probably the first person who actually brought a mass spec into the operation room, and they have lots of publications that they were able to really use a biomarker to aid the surgeon to guide the surgery in removing brain tumors. And so we started a collaboration. The current infrastructure in their lab is that when, for example, the surgeon is doing the surgery, simultaneously some of the tissue is given for mass spec analysis, and at the same time a pathology, basically a biopsy is requested, which take at least like 30 minutes, and they cross examine the results. And they had interesting findings that just by monitoring one single molecule, they can very accurately identify that if it's cancer or not. And sometimes this is something like basically the pathology, the way it works is that you basically cut the tissue and dye that, and a pathologist, who basically a very experienced person, just looks at it under a microscope and from the experience tells that, oh, it's cancer or not. So obviously it can be limits that, for example, if there's like just not enough to be able to visually identify that. With mass spec, it's like the sensitivities that we have with mass spec, you can basically detect like parts per trillion concentration of.
Currently, that's the issue with pathology right now, right? Is like you can have false positives, false negatives, because it's so subjective. Whereas if we put that diagnosis in the hands of a mass spectrometer, I'm not saying there also couldn't be issues there, but it's more objective. It's more yes or no. Yes, we have these molecules or these ions, or no, we don't. So yes, there's cancer, or no, there's not. So I think it creates a tremendous opportunity for the medical field and for patients, and I think it's really, really only the beginning on what we're going to see as far as applications of mass spectrometry in the operating room, but also more in the medical field. So it's really exciting. So why don't you describe your SPION device and some of the other technology that you've used for NASA? And remember, SPION is spelled SPION. Look it up. Do a Google search. You'll find it. Go to tracematters.com. You'll find it on Maz's website. But describe your NASA award. What's the award for? And how is mass spectrometry used in space? And then the applications of mass spectrometry in the SPION device in space and with NASA. Describe all of that whole story. And you talked about that's kind of how you started your company. So describe that.
Yeah, basically almost like any mission that NASA has, probably there's a mass spec, and this started from back in 1960s. That like for anything that you want to really see the chemistry, you need to have a mass spec. And again, mass specs, they're very sensitive instruments. That probably a good example is that a similar instrument is used at the airports for explosive detection. So they're so sensitive that if you have just few molecules, these devices, they can detect that. And that's why NASA has been using these for really seeing the chemistry on all of the missions. And basically, it's the most reliable instrument to be able to get really results with high fidelity, to be able to just make a scientific judgment based on these results. And yeah, I started working with NASA. It's basically to be able to learn from them and also help them make the next generation technologies. And this award that I got, it's mostly there was a call for new innovative technologies for mass spectrometry so that they can build the next generation instruments. And I participated, and we had the chance to present that in 3 rounds. And finally, we make it to the final round, and we got the award, which is really exciting because having that recognition from NASA, it feels really good.
Well, congratulations. And can you tell the story about wanting to work with NASA and your persistence there and how it worked out for you?
Yeah, I basically working with NASA, the moment you start learning about mass specs, you learn that NASA uses a lot of mass specs. And just by using a mass spec, you see how complex that is. And you see, for example, these companies, probably the service contracts is like tens of thousands of dollars per year just to keep the mass spec up and running. And probably I have to call the company once in a while to service the mass spec. But again, the mass specs that NASA makes, they send it to Mars, and it's working and sending us data after 5 years. So you see, you become to recognize that, wow, that's an engineering really wonder that they make something that complex so robust that in the extreme temperatures still it's working without any service call. So there should be something there to be learned. So that's why I started really looking at different groups that NASA has who makes mass specs, and I noticed that it's in Goddard, and back then I was in DC, and I started reading their papers, and I sent an email to one of their scientists that I really liked his work and wanted to work with him. And obviously these guys, they're super busy. It's like probably they receive tons of emails every day. So I send an email, not to just every once in a while, not to bother him, but to just remind him that I really want to work with you. But again, it's really difficult to break into that circle because they're really focused on really important things. And the opportunity that I saw there, that was that they're making these great technologies, but they don't have time to really bring them to the market so that others can also benefit from that. And so they're jumping from one mission to another. Again, it's a very hectic schedule. So I saw an opportunity that, okay, so I can learn from them and be able to bring some of those great technologies to for use by regular people who can really benefit from these technologies. And from there I started really working with them, and it took some time, probably 10 years, to be able to have their attention. But finally, I had their attention, and we're working on a couple of projects together.
That's persistence. So you never gave up. I think that's really, really incredible. So I want to dig into some more of the science here, because I want to hear your expert advice. And so one of the things that you talked about is, we have to control ions in a vacuum. And I, in general, agree with you. And I believe me, I do not know the physics like you do. I'm an applications guy. I like to know that things work, and I like to apply it. And I love to listen how you guys build stuff. But being able to do it the way you guys do it, no. But I love the equations and everything. So you talk about, having to have them in a vacuum. Yet we know ion mobility mass spectrometry exists, and NASA uses a lot of ion mobility, if it's my understanding correct.
Yes.
Yeah. So I love the future of mass spectrometry. I really do. The biggest downfall with mass spectrometry, when we're going to start using it in a wide scale, including it for personalized medicine, I do believe someday we're going to see mass spectrometers in a Walgreens and a CVS. I think we might even have applications for them in handheld devices for biomarker monitoring at home, possibly. But the issue is this: you have to have a big vacuum pump. So what can we do? Have you ever thought about that?
That's actually how it started, and I learned it over the years. So I started, basically my interest was really on making like miniature mass spectrometers. But over time, I'm not giving up on the idea, but I can say that I've shifted my focus, because I see that I can help in other areas. Because from again, we got this NASA I-Corps, we got into NASA I-Corps program to really go and talk to the end users and customers. So we did 100 interviews with many companies, with like startup companies making mini mass specs, and really try to dig deep into what the state is. And my understanding is that the mini mass spec market hasn't picked up yet, because really what you're doing there, you're reducing the size. Probably you're not able to reduce the cost that much, so it's still going to be expensive. So but you're compromising the performance. And from what I learned in mass spec probably market, it's the most important thing that customers care about is the performance. So if they're buying like $1 million, like they're spending a lot of money on mass specs, and they buy the best ones, it's just the performance. It's not anything else. And by reducing the size and making mini mass specs, you're compromising the performance. Plus, these mass specs that you see on the market, it's like many scientists, they've spent decades and decades and decades on them. So they are really, it's like, again, the analogy with phones, it's like you thinking about like the first iPhone and the iPhone 12, that it's a lot of improvement that took like probably 10 years, more than 10 years for a company like Apple to get there. And like Thermo Fisher, Agilent, these big companies, they've spent like really big teams on these types of mass specs, and really making something small that's going to deliver the same performance, and it's going to be difficult. So I thought maybe instead of just looking at the problem from that perspective, that's kind of also the how Spion got started. It's like, okay, let's look what they did and let's see how we can improve that. For example, one way of, usually the way people see that, it's like to bring the mass spec into hospitals and medical field and bedside application, you have to make it small. And I thought maybe if you make it small, it's probably for medical application. It's probably Thermo Fisher. It's the most suitable to make a medical device like that. But instead of that, what if we keep the same mass spec, we keep it behind the wall, and just we transfer the ions, and that way we get the performance plus we solve the problem.
Well, what's interesting is we think about these bedside devices and you've probably followed some of the science, and I think it's still intriguing, but lab on a chip and all these kind of things, because as well as I do, you can make a mass spectrometer this big, right? But your vacuum pump's still going to be this big.
Yeah, the vacuum pump is something that NASA probably doesn't have that problem, because mostly it's like the space you get free vacuum, free high quality, like zero power vacuum. But here it's like on Earth, like you're gonna need huge pumps, and those pumps, it's basically I also spent like probably 6 months to a year researching vacuum technologies. Wow. I couldn't find anything that I think it's kind of, at least with vacuum, I thought maybe there's nothing there to be improved. And if it's something there, it's going to be like companies like Pfeiffer who really focus on vacuum pumps. But again, I don't see an easy solution for vacuum. But the only solution that I was able to find, I should mention that it was something like vacuum on demand. That, for example, mass specs, you have them on running all the time. So the vacuum is on. But the amount of time that you use for analysis, probably it's milliseconds. So probably if someone can produce a vacuum for like on demand in that millisecond time frame, that would probably be a good idea. But again, I couldn't find anything.
That's a really good idea. I've never thought about that, because you really don't need the vacuum 99% of the time.
Yeah. If you're not like the analysis, like when you have ions in the system, that's when you want to have vacuum.
Well, and you think about, for example, chromatography and bioanalysis is what we do and what my company does. But let's just say you do have ions in the system and you're sampling those ions, but you're only interested in some ions that are coming through at 0.1 second or whatever.
Yeah.
So that's really interesting. So what do you think of ion pumps? I don't know anything about them. I've heard some people with NASA develop ion pumps to make them smaller vacuum pumps, which I don't know why you'd have to do that in space, because you just, you use your space as the vacuum. But are you familiar with ion pumps?
Yeah, I'm familiar. Probably it's a good idea to talk about like different pressure regimes and different pumping requirements. For example, if you want to go from atmospheric pressure to 1 torr, you need to have a roughing pump, a mechanical pump with pistons that basically pump out like a compressor, like reverse compressor type thing. Then from that vacuum to go to 10 to the negative 5, 6, 7 torr, we usually use something called a turbomolecular pump. That's a very fast fan that it's just a fan that speeds like at probably 100,000, like 1,000 rotations per second to basically push out the air. And after that, like these pumps, they have like an effective regime that after that they're not effective anymore. And after that, they probably use ion pumps. And ion pumps, from what I know, it's like they trap remaining molecules in a piece of, for example, titanium or something. So really, they don't have that much of a high capacity. They if you want to reach from 10 to negative 7 to 10 to negative 13, probably you need an ion pump. And you have to think about the molecules, like probably the mean free path of ions or molecules is a good way of just visualizing this, that in 10 to negative 5 to 7 torr, probably the mean free path is like tens of hundreds of meters. It means that if an ion is traveling in that pressure, on average, in every 10 or like 100 meters, there's a chance that on average, it's going to hit another molecule. So you can imagine that, it's like in 10 meters, we only have one molecule. And ion pumps are effective in just capturing and catching and trapping those tiny molecules that are remaining to be able to reach to high vacuums.
You still need a turbomolecular pump to get to the initial stage of a certain vacuum.
Exactly. So like like if you're going down in the pressure, then you have to first use turbo. You have to go step by step.
Okay.
Like if you turn on a turbo pump at atmospheric pressure, it's not going to give you any vacuum, and after a while, it's going to heat up and burn.
I see. I understand. Okay, excellent. Well, thank you for that. So what do you think, before we get to our final two questions, which are on all my podcasts, what do you think of the future of ion mobility spectrometry?
Ion mobility, I think the future, probably it's going to replace LC. Because it's like down the road, I don't know when it's going to happen. If we find we also have problems with ion sources that probably you're also, you know better than me, that we have ion suppression and many problems. So we don't have the ideal ion source yet. And LC is kind of compensating for lack of an ideal ion source. I think eventually ion mobility is really picking up. And the SPION also can provide ion mobility. It's kind of the same structure that we've made it flexible. So probably it's gonna happen at some point that ion mobility is gaining momentum, and I think it deserves the momentum. And we're gonna see more and more. And at some point after that, the problems with the ion source is solved, I think probably LCMS it's not going to be used that much.
I know what you're saying. Now here's, I still think that we have a ways to go, and it might not even happen in our lifetime, but the ion suppression issue can be solved by going to micro, submicro, and nanoflow. Then you don't have as much of you have equimolar responses and so on and so forth. So I think that you can solve that. And I agree with you. LC is not that much of a high resolution separation device, not huge really, even compared to GC or capillary electrophoresis or something. It's pretty low resolution. And I think ion mobility can compete with it at that resolution. So I agree with you, and it's very, very interesting. So we'll watch it.
I think it's more, the most important problem with LC is the time, which basically everything going faster and faster. Mass specs, like the bottleneck is the LC. Mass spec can give you the results like in milliseconds, like in seconds. But it's that timing that it's just the LC is kind of, it's slow. It's like we're starting to see like faster and faster LCs, but I think fundamentally ion mobility, it's it's on the right foundation to be able to replace the LC. But as you said, we might not see that in our lifetime, but down the road,
ion mobility has issues too with cross-sectional area, reproducibility, so did LC in the 1960s. And so we've come a long way. So it'll be interesting to see. So this has been fascinating. I could talk to you for hours, and this won't be the last time we talk. So a couple of questions I have on all my podcasts as we start to wrap this up is our theme is never be outworked. And obviously you've talked about some of your persistence, and we see your passion. We see your passion for chemistry, for mass spectrometry, for helping people. And that's what entrepreneurs do. They solve problems, and you're doing that. So congratulations. How would you say the never be outworked mindset applies in your life? Can you tell us more about that?
It's just everything is about that, because again, it's when I started, I've never built a mass spec, and wow. Basically, I've start from somewhere and work harder than anyone. So probably that's the only way that you can make it, unless you're lucky. That probably I don't know if I'm a lucky person or not, but you can't rely just on luck. It's just only.
Wait. Let's stop there.
Yeah.
The harder you work, the luckier you get.
Probably. Even if you're not lucky, if you have the worst luck in the world, you can work hard and you can just be successful and compensate for being an unlucky person. So what I'm trying to say that it's just the only thing that you can control, it's just working hard.
Absolutely.
Working harder than anybody else. Maybe someone is lucky; they're just with minimal efforts, they can get ahead of you. But the only thing that's out of your control, the only thing that you can control, is just working hard. And basically, it probably, in my experience, it works. And it's just, I've seen that myself. That there's a 10,000 hour rule that if whatever you want to do, you have to spend 10,000 hours and you become an expert in that.
Absolutely.
And it usually takes 5 years, but if you start working like overnight, weekends and everything, you can reduce that to 3.5 years. And I did that. And really at the end of that 3 to 3.5 years, I started seeing things that I was not able to see. For example, Spion was one of them, that you really become to understand. And like, if you're playing the piano, you don't look at the note. It's just, you just play. And that happens. And that's, again, it's just by working hard and not giving up.
Not giving up, working hard. I love your mindset and what you talked about when you play the piano, and it just what they call it is a flow state. They call it just flows. So I imagine that these things just flow with you now, and how Mazdaks work and how Spion works and how to build things and how to solve these types of problems with mass spectrometry. So really good job. That the only thing you can control is how hard you work. And I love that. One of the things that we've talked a lot about on this podcast is there's actually two things you can control in your life. One is effort. That's how hard you work. And the other one is attitude. And by the way, yours are both superb.
Oh, thank you. Yeah.
I love your mindset. I love it. You're passionate, you're positive, you're optimistic. So, because I think people not being an entrepreneur, and a lot of people, I don't want to be negative here, I want to be positive, but a lot of people that haven't gone through what you've gone through, they can certainly look up on your life and they can say a lot of negative things. They could say, well, he's lucky, or this, that, and this, here's why it happened. But those are also the people that have never tried. They've never tried. They sit back and they just judge people. And I can tell you don't do that. The stories that you're not really telling that I know are there are your struggles. And that's probably a whole different podcast. We're going to have the last question here, so you get to talk about one of them. But people don't realize it as an entrepreneur, as a scientist, as a father, as we talk about, especially in social media, all of our successes, but they don't know of your struggles. And I bet you have had a lot of them. And that takes us into the next question. Give an example of an apparent failure in your life that actually created more success for you. And I'll just give you my own personal opinion on failures. I don't really believe in failures. I have a feeling you don't either.
Yeah.
I believe you learn from a mistake. It's like science. You learn from a mistake, you create a new hypothesis, and you move on and you do a new experiment. But what apparent failure in your life actually created more success for you?
Actually, the way, if I want to say that my whole life has been failure, it's just probably, I don't know who said that first, but you have to just make it once. You can fail, and make it once, and then you can kind of you'd be able to make it. And probably the people who know me, I've failed almost at everything, and probably I don't consider myself a lucky person. But again, it's the failure, as you said. It's just you learn. It's something that didn't work. Like even with mass spec instrumentation, it's just 99.9% is failure. 99% it's not working, and you're trying to understand why it's not it's not working, and then you learn and put a check mark that, okay, I learned this. If I want to work, I need to do this. And especially mass spec, it's a good example that without making those mistakes, you're not going to learn. Because when I was making a mass spec, it was simple that, okay, do this, it's going to work. but there was a million things that didn't work and it failed, and I learned that finally I was able to produce a functional mass spec. So all I can say that is that yeah, it's failure. It's life probably. It's supposed
It
to be a
is. Well,
failure, and you have to just fight that and works against that, and you have to just make it once.
your philosophy is great. I don't remember exactly the number that Thomas Edison used, but Thomas Edison said something like this. Obviously, one of the greatest inventors of all time. He knew 999 ways how to not make a light bulb. Something,
Yeah,
you know.
I think that's true. If it's like the physics, it's not a time machine that it's really impossible to make, but it's probably yeah, anything you want to do, if it's physically possible, you're going to be able to make that.
Well, and that's what I like about mass spectrometry and chromatography, by the way, is that yes, there are rules, there are physics involved, and there are equations. But there's also, whereas I think when you talk about NMR, MRIs, spectroscopy, this is in my opinion, and I probably don't know those deep enough. There are hard and fast rules on what works. With mass spectrometry and chromatography, you can guess, but you don't know until you try it.
Exactly. That's so true. That's so true. Because with mass spectrometry, um, it's very multidisciplinary, because you need to know vacuum systems, you need to know high voltage, high frequency, low current measurement, you need to learn about noise. Like in all the fields, you're going to be pushed to the limit to be able to make some functional mass spec. And it's interesting that it's like in the fields that, for example, you mentioned, there's a consensus of most of the phenomena that it's used to make a functional unit. But for mass spectrometry, you can go to the conferences today and people would just disagree on something totally yeah. So
yeah, but this has been great. This has been wonderful. Thank you for joining, and let's keep in touch for sure. We're going to keep in touch, and congratulations again on your NASA award. And let's keep in touch. And for all you viewers out there, thank you for all of your engagements on social media. Thank you for following my podcast. Thank you for all your positive comments on saying, "Hey, keep it up on social media." I love you say I'm an inspirational to you. You are inspirational to me. So thank you very, very much for your viewership and your listenership. And again, find me on Instagram, find me on LinkedIn, find me on Facebook. You can also follow all my podcasts on YouTube, on iTunes, on SoundCloud, on the Spotify. Go to my website at drsneedham.com. You can find more information there as well. And just Maz, thank you very, very much. Let's keep in touch, and you keep building those mass spectrometers. More importantly, keep inspiring, keep the passion, keep the perseverance, and the future is so bright for you. Thank you very, very much, my friend, and thank you, and we will talk soon.
thank you, Shane. Thank you for having me.
Thank you. Thank you.
Pleasure. Thank you.